Good morning.
Hello. Can you hear me?
Yes, I can hear you. I see your screen.
Is it working?
I see right now just like the File Explorer window with your files in it.
Oh, okay. How do I thought I hit on the PowerPoints. You don't see the PowerPoint?
I don't know, just the file or the two files.
How do I, it says I'm sharing and I open the file. What do I hit there?
So stop screen sharing.
Stop it, okay.
And then start again and try to choose the PowerPoints. Or you can choose a whole screen if you want.
Is that clear now?
Yes.
You see it now?
I see it now. Do you want to try to put it in present?
Okay, does that work?
Yes, looks perfect.
All right, it's good. So
Great.
you guys are, how long have you been there? You a postdoc?
I'm a grad student and Kai is a postdoc.
All right, so who's your advisor?
Chris Zappa, who actually just logged on.
Hey, Chris.
Hey, Raghu, how you doing?
All right, man. How are you?
Good.
How is everything?
Pretty good.
Are you working from the ocean or are you working from home?
I'm going to the office right now.
Oh yeah, okay. That's good. all the instruments are working?
Everything's working. Yeah, we haven't been we kind of finished up everything right before COVID started back in
okay.
Nice. A cruise in January.
Oh, so you got home just in time for the lockdown?
Just in time for the lockdown, yep.
Yeah, we got a little lucky with our timing.
Where were you? Atlantic?
We're in the Pacific. Yeah.
Oh yeah. Did you get ONR money for the Indian Ocean, Arabian Sea?
No. This was from the Schmidt Ocean Institute on the Falcor.
Oh, okay. Where, with the Western Pacific or North or?
Western Pacific, right near Fiji.
Oh, Fiji. Okay.
Yep.
Wow. Okay. Nice. So whatever happened with the Indian Ocean plans under Scott Harper?
I don't know. What did happen with that?
You're on the gravy boat, right?
No. Something.
Yeah, I'm just joking.
Are you in the US or are you in India? I remember you went to India for a while.
No, I'm in India still more than 2 years now. Nope. I don't feel like coming back. So. Yeah.
How are things there?
Some things are okay. Some things are. I'm basically trying to take care of my father, who's not doing so well. But
that's too bad.
That's life.
Yeah.
Yeah. So Kai, who's Kai's advisor? Sorry, go ahead, Chris.
Go ahead. No, I was just gonna say my parents are getting old too, and it's hard not being able to be up there. But I have lots of siblings live up there, so that helps a lot.
Is it in Washington? Where are they?
No, it's in Boston.
Ah, Boston. Okay. Yeah. Yeah, it's rough being. Yeah. Anyway, so, but one has to manage somehow. Yeah.
Yeah.
So who's Kai's advisor?
Kai, you there?
I think Kai is not. Kai's just put his picture up and gone home.
I know he was finishing another meeting, so he may be wrapping that up still.
So this seminar series has been running from the beginning of the semester?
Yeah.
Did you guys start on time, everything, the semester?
Yeah, the seminar series has been pretty successful.
Yeah.
We've only once had a significant issue with getting the slides to show up for one presenter, but other than that, it's been very seamless.
Yeah. Yeah, no, I'm always nervous about these things because I tried it last time from the iPad and it kind of became messy. So I used my laptop this time.
Yeah. Well, if we've gotten to this point, usually we're good to go.
Yeah, let's hope. Yeah, and I visit almost every year and a lot of my buddies show up. I don't know if they'll log in. Let's see.
I hope so.
So what's your thesis topic?
I'm just finishing up this is just a master's thesis. I've finished that and I'm working on a revision for JGR Oceans. And that was a project in Arctic Alaska, working with an indigenous community there. Looking at winter, we're quantifying the heat budget of the sea ice up there in the winter and looking at the role of river outflow in coastal sea ice thermodynamics.
Really? Wow.
Yeah.
I was in Barrow, Alaska a couple of years ago. That was fun.
Oh, nice. Yeah, this is Kotzebue, so just a bit south of there. Yeah. Pretty close by Alaska sizes.
Nice. So you had flux array or something you're measuring?
Under ice. We had
under ice. Okay.
Yeah, ADCP and a thermistor chain under the ice.
Nice.
Yeah. And then we just we had like just bulk measurements of atmospheric parameters.
How long was it there?
It was out for 3.5 months, through the dead of winter. And then we pulled it right before the ice started melting so that we could get the data back.
Yeah. Wow, you got good data then.
Yeah.
Nice.
It's a really interesting time series. It was in a river outflow channel, hence looking at the river's influence.
So you have salinity?
Yeah, so they're, full salinity range, like fresh water all the way to 32. So nice. Lots of interesting stuff to look at and pretty complicated data set. It's been really fun.
Had little convection going on, or was it just?
Pretty much just like either it's flowing one way or it's flowing the other way. And the salinity just reflects that. Mm-hmm. Yeah.
Nice.
Morning, Arnold.
Yeah, morning. And Raghu, where are you?
Hey, Arnold.
Now or Maryland? Not that makes a difference.
Huh? I'm in India.
Oh. Yeah. So what time is it there now? About midnight or something? Or
no, it's like getting to 9:30 by now. So seminar starts at 9:30.
Not bad. Yeah.
That's why I agreed, because somebody had asked me for a 2:30 a.m. seminar.
Now, one of the problems now with Zoom, because so much I work is in Indonesia or in India, Sri Lanka. Yeah. So I have Zoom meetings at 11 o'clock midnight now, and then I got Zoom meetings during the day.
Yeah.
Save time traveling by airplane, but there's more time sitting in front of the computer.
Yeah.
I have a nice introduction for you. It's nice and it's friendly, and I just don't hope you take it the wrong way. You will.
Depending on how you introduce me, I'm going to tune my jokes about you. So.
Oh, no. All right, let me change it. All right, okay, signing on.
So you're just collecting awards now every week?
That's all I'm doing. I know it gets tiresome.
I know.
Then I got to give this spur drop lecture at AGU.
That's right. Yeah.
I got to actually do work.
Yeah. You win so much, you get tired of winning.
You get tired of it. Yeah, didn't Trump say something like that? Boy, I'm glad he lost. All right, let's see. Oh, you got my name right there on your first slide, huh? The Mixmaster.
That's right.
Boiler box. Boiler box. Well, I think that's all right too.
I think you need to do more in the maritime continent. You're slowing down, Arnold.
I thought I did everything already.
No, now you went into the Indian Ocean. So
yes, and yeah, but Murtugudde oscillations will probably bring me back across the maritime continent, particularly what you're going to talk about today, because I have been looking a bit into that, a relationship to the interannual variability of the South Pacific convergence zone. There's some interesting changes there, and I often wonder what MJO role plays in that. Or the MJOs that those kind of oscillations you see in the South China Sea or Bay of Bengal. All right. Anyway, I look forward to your talk, and I have here written out, my introduction.
It's a long one.
It goes on and on and on. You're not going to have much time.
It's like a eulogy.
Oh boy. What time is it? 28.
So everything is still online, right? Classes and so on?
Yeah. Yes, and it looks some of it's hybrid where a few of the students can show up in class, but like the oceanography class this year is 14 people registered and there's one in class. All the others are remote. And that's going to go on until the spring, because there's no doubt that this is not going to get any better until well into the spring, even summer. So I'm just looking at the COVID cases and actually India, which is going down in the last month or so.
Yeah, India just started magically dropping. I'm not sure what happened there.
Yeah,
I hope that's real.
Is it masked, or you think there might be, more immunity than we think there is?
Asia reacted very differently. I think so did Africa. Somehow there is something genetic.
Africa was very different. Yes, Africa was very different. But India was increasing quite rapidly. Then all of a sudden, it flattened.
Yeah, and then it started dropping. And there's no explanation, so who knows? Plus, winter has started. So in the north, they have a little bit of a second wave. So I don't know if that's going to come down to the south or not.
That too.
Yeah.
But when you say winter, isn't it, are people more inside in the winter months there? Certainly up north.
In the north, yeah. I mean, this is a La Nina winter, which tends to be harsher. So
I see.
Yeah, let's see what happens. I mean, we're still in November. December, January could be rough in the north, but I don't know what happens in the center and south. So, curious.
All right, let's see.
So when you're ready, guys.
We still have lots of people coming in, so I'll wait till that slows down.
Okay.
So you don't get back to the United States. Obviously, you can't travel very much anymore. So it's
Yeah, my leave was ending in August, but the university extended it by a year because of COVID. So I'm going to be sitting here till next August. And I'm actually trying to see if I can just stay back because I'm doing a lot of things in India, which I want to continue, but we'll see how it works out. I'm not young like you, Arnold.
Yeah, I'm still learning, you know, just sort of a mind of sort of an 8-year-old kind of now. It used to be up around 20 or 30. Now it's back down.
Yes.
We have to, well, I got too many people on here now. We can.
I think they're used to you.
Yeah, I know. Let's see, how do I see this? People who are on it.
I'm scared to get out and see who's logged in, but anyway, because I'm sharing the screen and something goes wrong.
Yeah, usually we have like about 30, 40 people, but you know, in this case, there's only about just me and you. I don't understand it. Don't understand it.
And you'll fall asleep soon anyways.
Yeah, I'll put on my, rather than have a live camera, I put on my picture in front of Disney World, you know, so. Let me show you my Disney World picture. There it is. Oh, yeah.
Oh, yeah. Is that Disney World? Oh.
Yeah, actually, that's my castle in France. Disney copied it for their park.
Yeah. The King of Morocco gave you a castle in France.
Yes.
King of Monaco, not Morocco.
That's right. Yeah. All right. Maybe we can begin. I don't know. Carsten, should we begin or what?
Give me 2 more minutes and then we'll get started. I'm still catching up with the waiting room.
Oh, that's right. That's right.
Yeah.
Oh, yeah.
People are still flowing in.
Yeah.
So I want to get them in.
The gateway.
Hi, Raghu.
Take these.
Hey, Mark, how are you?
Okay, good to see you.
Good to see you, Mark. How are you doing?
Okay. After you, I go to see the dentist. So
wow, that's
so
double torture.
I hope. Well, I expect better of you than that. I think that's a standard you could easily meet.
Yes. You know I do.
You should really though drill down.
Yeah.
You know.
Geez, Arnold.
The dentist next week.
Hi, Raghu. Good to see you.
Hey, Richard. What's going on, man?
Well, we're waiting to hear what you have to say.
Yeah.
I like your glasses.
Oh, thank you.
Hey, Raghu.
Adam.
Where are you? In India?
I'm in India.
Where?
In Mumbai, in Indian Institute of Technology.
Oh my gosh, for how long?
I've been here for 2 years.
Wow.
It's coming to an end. So, yeah. So I thought you left MJO and went into cyclones and hurricanes and stuff.
Still doing some MJO.
Sea level, yeah.
Hi, Raghu.
Hello.
Michaela here.
Michaela. Hey, how are you?
Good. Nice to see you.
Good to see you. Wow, this is awesome. Zoom is good.
Yeah.
Yeah, I think we can go ahead and get started. Arnold, if you want to kick things off.
Oh, all right. Yeah, I just have a short introduction. I think you'll know Raghu, so don't have to say too much, but I thought a few things to say, and they're nice things. So he's a professor at the University of Maryland, as you know, Department of Atmosphere and Ocean Science. He's a visiting professor in Indian Institute of Technology in Bombay, and he's been there for 2 years, he just said, and is now COVID is going to keep him there another year. He got his degree from Columbia in 1994 in mechanical engineering, School of Engineering. And his advisors were Facade, as he said, in mechanical engineering, and also Mark Kane in Lamont. In his website, Raghu says he studies the interaction between the physical world and life and explores the coevolution of life and climate. He uses data and model products to advance process and predictive understanding of the Earth system, especially at regional scales, with a focus on the role of the ocean in tropical climate variability at diurnal and decadal timescales. Published many articles, as you know, on the Indian Oceans linked to the Asian monsoon, including intra-seasonal variability, such as the Madden-Julian oscillations. Now, here comes the serious part. He has 196 publications, and his H index is 58. And I usually don't mention H index, but Raghu's always talking about his H index.
What?
I figure I should say something, otherwise he'll accuse me of being nasty, which he probably is going to do anyway. And he has many publications, as you all know, with OCP researchers, and he also has one with me that has 201 publications already. Anyway, but I want to tell everybody about the chance meeting we had. You remember that, Raghu? And
yes,
in January of 2017, I was coming out of the United Club room in the Bombay Airport, it's called Bombay Airport, and after drinking lots of wine there, getting my next flight to Sri Lanka. And a few doors down comes Raghu out of I guess it was the gym, the airport gym. And what an amazing, to meet him there, coming out the doors at the same time. And, so I said, what are the chances of this? And we just said hello, like it was nothing strange. And so I just think am I cursed? I can't get away from it. Is that what this is all about? Well, anyway, he's back today to give an OSA seminar, and MJO-Detours, the ocean's role and impact on the South Pacific Convergence Zone, which is an extraordinarily interesting topic. So Raghu, so zoom away, Raghu.
Thank you, Arnold. Yeah, so what can I say? Always great to give a talk to Lamont. Usually I love visiting and seeing people, but here we are. Good to see you all on Zoom as well. So this is basically a paper that just came out maybe 2 months ago from Zhao Lei, who actually did a postdoc at Lamont with Adam and did a PhD with me now. He's a prof at Jiao Tong University in Shanghai. The second paper on the impacts on SPCZ is just being revised, and hopefully that'll be finalized soon. So I'm going to just present a few results from that. And as you will see, it's basically adding another grain of sand, as Mark Kane always tells me, to the big pile of MJO's sand pile. Though this schematic here, I don't know how many of you already are familiar with MJO. I know a lot of the older guys are. For the students, if they're logged in, this is a schematic that has been used for a long time. I don't know if it actually came from Madden and Julian, but showing, you can see here on top, the longitudes, east longitude and west longitude. At the bottom, you see Africa and Indonesia and South America are identified. These convection centers are moving eastward, and they are shown roughly 5 days apart. It's showing the zonal vertical circulation, the tropopause, and then surface pressure, also mentioned as sea level pressure here. So this is very well known that it's got convective phase and dry phase and moves eastward at the intra-seasonal time scale, typically mentioned as 20 to 100 days, 20 to 60 days, various numbers get mentioned, but basically less than a season. And it has a strong seasonality. Ramage was fascinated by the maritime continent with data. He called it the boiler box, and he talked about just how much heat gets released there, about 5 meters of rain, I suppose, in a year. And Arnold calls it the mix master from the ocean side. And looking at a lot of the Indian Ocean, oops, my slides are not moving here. Okay, there we go. Looking at ENSO and Indian Ocean dipole and the monsoon, I'm now pretty much convinced that the maritime continent is really a huge center of action for all of tropical climate variability at various time scales. The typical time scales of intraannual variability also moves from quasi-biennial to the west of the maritime continent to kind of quasi-quadrennial to the east. So the ENSO timescale on the Pacific somehow transitions to a quasi-biennial timescale over the Indian Ocean. And there are nice papers by Harry Hendon and older ones by Neville Nichols that talk about how that timescale is generated over the Indonesian seas. But the previous figure is now shown more like this. We have color graphics, of course, but also these are what are called phases of MJO based on an index that was defined by Wheeler and Hendon back in 2004, which uses a combined EOF of OLR and zonal winds at 850 and 200 hectopascal. They take PC1 and PC2 of the combined EOF and define RMM1 and RMM2. I'm mentioning them separately because their MJO index, this is a real-time multivariate MJO index, RMM, and they do RMM1 squared plus RMM2 squared, and the square root of that. I'll show a phase diagram in a minute. But typically the convection originates about the western southern tropical Indian Ocean in the Western Hemisphere, as they call it. And you can see that it moves eastward, crosses over the Indonesian seas in these composite figures. But actually, when you look at the details, people typically average over 15 north to 15 south, and then argue that many of them don't cross the Indonesian seas, and some of them cross that get weaker, and so on. And I'm mentioning RMM1 and RMM2 separately because when you want to look at what's happening over the maritime continent, you cannot use the MJO index. You have to use RMM1 and RMM2 separately because over the maritime continent, convection is located there when RMM1 is maximum. So we have to kind of remember that. On the map, you see phase 1 is here or here, the Western Hemisphere, the Western Hemisphere, whatever they call it. 2 and 3 are over here, 4 and 5 over the Indonesian seas, and then 6 and 7 over the Western Pacific. Essentially, the temperatures get too cold over here, so the convection is not maintained anymore, but you get signatures in winds and vorticity that often travel all the way across the South American continent into the Atlantic, or the African continent back into the Indian Ocean. And some of them seem to get reignited over here, but many times they are just originating here. But lots of questions remain about MJO genesis, which I'm not going to get into. So here is how the RMM index is plotted. You can see there's phase 1, 2, 3, 4. So it goes counterclockwise. As you can see here, for example, going from I don't know, day 5, 10, 15, and so on. When it's here at the center, it's too weak to be characterized by this index, so it has to be here when it's strong. And the prediction of MJOs is now big business, as I will talk about in a minute. This is a new figure, a new paper from Yonoyama and Zhang, who have been very active in leading a lot of the years of the maritime continent kind of programs on MJO. And it's quite busy, but essentially MJO impacts and interactions, if you will, with ENSO has been studied for a long time. With the Indian Ocean dipole is a new thing. With the monsoon has been studied for a long time. ITCZ, of course. It's not always clear if MJO is some kind of a multiplicative noise that interacts with El Nino and gets stronger or weaker. But now the studies say that MJO can affect, of course, it has impact on the ITF as well, because it's passing over here and impacting the outflow as well as the inflow. And there are MJO-driven waves from the Indian Ocean, which come down as coastal Kelvin waves off of Sumatra and interact in the Lombok Strait and affect the outflow into the Indian Ocean and so on. But wildfires, sea ice, lightning, heat waves, even tornadoes and hurricanes and cyclones. So there's definitely a strong relation between cyclogenesis and MJO phases, which some of the nice work by Susanna Camargo and Adam Sobel and so on. In India, basically, my interest has been to look at the S2S forecasting. India has invested a lot in extended range forecasting and weather forecasting. And some of the skills are remarkably good. A lot of the extreme events I watch very carefully during the monsoon, and 1 to 3 day forecasts are quite reliable. Of course, decision making based on that is still got a long way to go, the last mile issues and so on. Even the extended range is being done now using the so-called GEFS from NCEP, the Global Ensemble Forecasting System, which is the forced atmosphere model. And under WCRP and WRP, there is now a very active group that is leading this subseasonal to seasonal prediction project with these objectives of improving forecast skills and understanding them on subseasonal to seasonal time scale, to promote initiatives to uptake operational centers and exploitation by the application. So I am somewhat focused on developing early warning systems for food, water, and health, and there's been some success in doing that. Just to add a little bit more from the Yoneyama and Chidong's paper, I'm not going to get into any of these theories, but there are several, which is not a good thing because that means we still don't understand many things. So Chidong boils them down to the skeleton theory, moisture mode theory, gravity wave theory, and the trio interaction theory. I'm just showing here the schematic from the trio interaction because it kind of mentions everything that every theory uses, which is obviously convection is very critical. So vertical motions and moisture recharging, if you will. And there are questions about whether the convergence happens frictionally at the surface layer, surface level, as shown here with the Kelvin waves and Rossby waves. So the waves are also a very critical part of the MJO in all the theories in general. And the waves don't travel like free waves, so they're called convectively coupled waves and so on and so forth, which obviously I'm not an expert on, but it has a very well-defined vertical structure. And Bin Wang has been pushing this trio interaction theory, which has lots of details in them. But as I said, so many theories generally means there are many questions that are still not answered as to exactly where the scale selection comes from. So from the monsoon point of view, I'm also interested in exactly what the seasonality of it means, because typically MJO is strong from October to April, and then from May to September, we have the monsoon intra-seasonal oscillation. So whether that is related to, oops, sorry, this keeps moving. Whether that is related to the IPCZ moving or whether it's just moving into the summer hemisphere and so on, that those are not obvious. But that may give us a way to think about why during ENSO years, monsoon droughts may happen. Is that because MJOs remain strong and mesos get weakened? But correlations don't seem to show that obviously. So we have to figure out how the seasonality is affected by the monsoon, by the ENSO. And we also don't know how monsoon itself affects ENSO during the monsoon season, okay? But this is a figure from Feng et al., but you find many such figures from Adam's papers, DeYoun's papers, and so on, which is showing the 15 south to 15, here it is 10 south, 10 north, averaged 20 to 90 day filtered OLR anomalies. And you can see that the maritime continent is around here. And some of the MJOs seem to propagate right across, but they get weaker over the maritime continent. And some of them re-amplify over the Western Pacific. But some of them seem to get stalled over here. And again, there are many ideas as to why there may be a barrier effect of the maritime continent on the eastward propagation of the MJOs. And the most obvious one is the argument that all these orographies over Sumatra and various other islands, there are literally some 20,000 islands here, I think. The just physical barrier is considered one of the potential causes. And then there is the huge land-sea contrast. Adam argues that land has got very low heat capacity, obviously, and its diurnal cycle tends to be very strong. So maybe the energy is being taken away by the diurnal cycle, and MJO doesn't get the energy when it's moving across here. But there are also these so-called detoured MJOs. So when we average over 10 south, 10 north, maybe we weaken the signal and think they are stalled because they're actually going south, maybe further south than 10 south. If so, what are the processes that may be driving these detours? That's a main question, and that's what I will kind of try to focus on. This is a paper from DeYoun when he was Adam's postdoc, I suppose, which talks about the propagating case and the non-propagating case, showing enhanced convection over the Indian Ocean sector. And there is the easterlies associated with the forced Kelvin wave, and there is an anomalous subsidence associated with this MJO timescale convection. So that is supposed to produce this poleward advection of moist static energy, which Adam loves moisture modes, I think. So he likes this moist static energy advection as a favorable process for allowing the propagation across the maritime continent. Charlotte DeMott also talks about Western Pacific Ocean impacts on preventing the propagation. When you don't have this moisture, the moist static energy advection process, the propagation doesn't seem to happen, okay? DeYoun has gone ahead and then has another paper where he argues, as I will talk a little bit more about why detours happen. This figure I made for one of a book chapter I wrote on the monsoon. And if you look at the ITCZ, which obviously is more in the Southern Hemisphere during the SON and DJF season, which is the typical MJO season, it seems like maybe there is something to do with the ITCZ, why MJOs would come across in the deep tropics in the Indian sector and then detour towards the Java and Northern Australia region before crossing over into the SPCZ region. By the same token, one could argue that maybe during June, July, August, where the ITCZ takes a very complicated kind of character with the continental convergence zone. And the ocean is so warm that the marine ITCZ doesn't disappear. So you end up with kind of a split ITCZ over there with the demise of the ITCZ over the cold upwelling region of the Somali coast. So that's for another day, but I think ITCZ is somehow a big part of this. Getting into now the results from the Detour paper that came out in Journal of Climate a month or so ago. This is showing OLR, intra-seasonal OLR. So you do the standard filtering of 2200 days and look at the anomalies. We call this as the Southern Tropical MJO event, and this is the Northern Equatorial MJO event. The boxes are shown here in the bottom panel, which are basically lifted from Deyun's definition of the northern and southern boxes. And you can see that there are some events, obviously minimum OLR is deep convection, as most of you know. When the northern events happen, there is no such strong convection anomaly here. Obviously, when the MJO detours, it's going through here, and there is deep convection happening here. So Deyun's idea was that there is a background seasonal moisture, and then the Australian monsoon onset happens. And you have MJO-related winds here, which can advect meridionally and mostly zonally, and load the atmosphere with moisture and moistatic energy and trigger convection. So he didn't look at the ocean's role. So what we are doing is essentially look at the contribution from the ocean. So it doesn't say necessarily that Deyun is wrong, but it's just, one can think of it as the ocean half of why there may be this buildup of the moist static energy in the south. And the key question then is whether, obviously when you say ocean role, something to do with the SST, then I'll talk in a bit that the key question is whether the MJOs that are propagating here in the Indian Ocean send off obviously Kelvin waves, which can hit the coast and go poleward as coastal Kelvin waves. A lot of energy comes down here along Sumatra and Java, as I mentioned, and they can create SST anomalies here. It's a question whether MJOs themselves can create a condition for detouring themselves. But in that case, the key question is, why don't all the MJOs then detour? Why do only a certain percentage of them detour? So the way we did it was to identify detoured MJOs in this way, where we just took the daily OLR difference between the northern box and the southern box. So when the convection is in the southern box, this difference will obviously be positive, and when it's passing along the equator, it will be negative. So you identify the southern detoured MJOs by the OLR being greater than the mean plus minus one standard deviation. So the blues and the reds here are the detoured and non-detoured MJOs. And we also use RMM1 here because RMM1, as I mentioned before, has to be maximum over the maritime continent. We cannot use the RMM as defined in the MJO index because RMM2 corresponds to convection over other regions. We don't want to mix that. We want to stick to be sure that we are talking about the detour and convection or the maritime continent being maximum. Okay, so these are some Haug-Miller diagrams now where 0 is when the convection is maximum on the maritime continent. So these are the northern events averaged over 5 north, 5 south. And these are the composite, all of these are composites for 1980 to 2017 or so. These are the composite detoured events. Obviously, you can again see this character of somewhat of a weakening over the maritime continent before crossing over into the Western Pacific. And obviously, if you look in the equatorial box, the detoured MJOs don't show a signal. But if you look at 5 to 15 south, which is the box defined over here, then obviously you see a very strong convection signal over the maritime continent. Okay, that's just confirming what I already said. Now, if you look at the humidity, we just did the budgets for humidity and moist static energy, and look at the interseasonal wind anomalies associated with the southern tropical events and northern events and their difference. You can again kind of see what is very consistent with what Deyun had reported, that there is moisture loading here, and associated with that, you have this cyclonic circulation, okay? So then the question is, what is the role of the ocean in producing this? How do you get here? So do you transition from there to there, and whether ocean has a role to play in that? That's kind of what was the focus. Looking again at going from the peak convection day to 4 or 5 pentads before and 5 pentads after. This is showing in colors low level, oops, I cannot see my own captions here. Moist static energy, and the contours are moist static energies, and I think the colors are OLR. Lei, are you there? I should have remembered it. But anyway, you can see that prior to the peak convection of about 10 days, there is a solid the colors are the divergence. So there is a convergence of humidity and moist static energy that builds up in the atmosphere, which is essential for obviously driving convection. And it is dominated by the convergence, as you can see here, and the loading happens well before the convection. So what is the sea surface temperature signal associated with that? Okay, so this is again just showing the intraseasonal moist static energy for the southern events. You can see 10 days before, peak of the convection and transitioning into the Western Hemisphere, Western Pacific from day 0 onwards. Obviously, the northern events don't show that. Oops. How do I get rid of this? Anyway. So northern events don't show that moist static energy peak here, and this is just the difference, and these dots here mean that the difference is statistically significant, okay? I hope that's pretty convincing. If you now look at the sea surface temperature, so this paper shows going back to -25 days, but I just picked day -10, day -5, and day 0 with the OLR shown in, OLR difference shown in the red bold contours. And you can see several features here. The convection is active over the Indian Ocean, as you can expect, well before the sea surface temperatures are warm here already by day -10, okay? So there is some kind of a preconditioning set up by the ocean, okay? And as the convection moves over to the warm SSTs, the peak convection happens here, and then the SST signal disappears on day 0. So the ocean preconditioning happens before, and when convection happens, actually the ocean loses its warm anomaly. The other important thing is that there is not a whole lot of sea surface temperature signal over the Indian Ocean prior, it's only here. So some local process must be happening, okay? So it's not, it doesn't preclude the MJO related Kelvin waves coming down here and creating the warming. I'll come back to that. In fact, that does happen, but in these detoured MJO events, it seems like something is locally producing the sea surface temperature warming to get the system ready to detour from the equatorial region into the deep tropics. The processes become a little bit clearer here. It looks messy, but just bear with me. The white lines here are the climatological winds. So there are basically westerlies over the region here. There are these southeasterly trade winds that are persistent in the Indian Ocean, as we know. But over these regions, you have the equatorial westerlies. Indian Ocean is unique in that way that it doesn't have the trade winds. It has westerlies, and there are westerlies also over this region between Australia and Java. The MJO-related anomalies are basically subtracting from the mean winds to the north, and they are adding to the mean winds. They're subtracting in the south, and they are adding in the north. So the latent heat loss is increased here. So the warming is favored to move south, basically because the classic wind evaporation SST feedback happens. So the cyclonic circulation over a warm SST basically means that the ocean is driving the atmosphere here. Otherwise, you would get immediate cooling of the sea surface temperatures if you had atmosphere driving the ocean. So that's one thing to remember. The other key thing to remember is that the MJO-related cyclonic winds themselves are able to create a increased latent heat loss to the north, so cool the sea surface temperatures, and reduce the latent heat loss to the south and favor the southward movement of the warm SSTs, okay? That's kind of a bit descriptive in the sense we didn't do a complete heat budget. We haven't looked at all the other players here like the Indonesian through flow or the Kelvin waves, as I mentioned, coming from this side. But nonetheless, the local wind evaporation SST feedback is fairly clear when you look at the MJO-related circulation and the background winds. So then, as I raised before, these SST anomalies do occur because of the MJOs generated by the MJOs, where the Kelvin waves generated by the MJOs when they are propagating here eastward. The Kelvin waves come down and create interactions with the Indonesian through flow. And there are seasonalities here. Feng and Weifels, for example, have talked about the instabilities generated here in the summer months before the MJOs peak in the boreal summer months, which is direction of available potential energy from here. And then they talk about Rossby waves propagating from that instability. Lei, when he was a student, did some work to show that during the fall winter months, the MJO Kelvin waves, in fact, do interact with the through flow, which is now past its peak, because the Indonesian through flow peak happens in June, July, August. By fall winter months, it's it's reducing to its minimum. Nonetheless, you produce baroclinic instability here, which propagates Rossby waves as well. And he shows with the heat budget that actually you affect the thermocline dome that is here, as well as the heat budget and the sea surface temperatures. So the conjecture there was that maybe there is some kind of a loop here where MJOs are generating Kelvin waves, interacting with the through flow, producing Rossby waves that go back and affect the sea surface temperatures here, which is key because this is the strongest region for MJO genesis. But this propagation here takes 12 to 24 months. So it's not clear on what time scale they may be interacting with each other or feeding back to each other, and whether it would be a positive feedback, in which case you have to explain what breaks that cycle and so on. So that story is not quite complete. But essentially the argument would be that this region is well known for its various things, like this is a very unique region where bluefin tuna lay their eggs because they look for very special ocean conditions. Looks like the through flow and the MJOs and maybe this local process of wind evaporation SST feedback generate some special conditions here which favor MJO-Detour. As I said, if it is just MJO Kelvin waves, then it is not clear why every MJO doesn't do it. What is special about some MJOs that they create a SST anomaly that detours them? So that question also has to be answered. Obviously, you cannot give a talk at Lamont without mentioning Arnold and his Indonesian through flow. And as you probably students have noticed, he changes the transport number every year, and we have to just accept it, obviously, Arnold, right? So here is the boreal summer circulation, and you can see where the warm SSTs are, and there is actually upwelling and cooling here. Remember, the Coriolis is to the left in the southern hemisphere. Whereas in the boreal winter months, the monsoonal circulation completely reverses. And Arnold's favorite thing is this transport here through the Karimata Strait of the fresher South China Sea waters, which he calls the freshwater plug, that actually blocks the flow of the Makassar Strait and cools the Indian Ocean instead of warming it. So it's not clear at this point whether that plays any role in this particular air-sea interaction and west feedbacks in this region. But we did look at the sea level variability in this region associated with these detoured and non-detoured MJOs. And you can see that at day -10, so day 0 is when the convection is maximum here, the sea level anomalies are lower here, which is unfavorable for this southward flow. So the freshwater plug need not happen in that case. Day -5, it gets even stronger. And you can see that the MJOs that move in the northern box have that freshwater plug kind of sea level anomaly. Whereas the composite events that are going through the southern box seem to disfavor this freshwater plug. So maybe the role for the intra-seasonal Indonesian through flow is important as well. That would explain why the SSTs don't have a signature in the Indian Ocean, and you mostly get the signature that seems to grow locally and move southward because of the wind evaporation SST feedback. Okay, so I will come back to this as a schematic after I finish the SPCZ story. Obviously, if the MJOs are coming through here and go across here, they must have an impact on the SPCZ. Okay, this is kind of noticed, but no quantification was done. Okay, so obviously, again, to make sure that we are tracking the MJOs that are detoured and then coming over here, you have to follow RMM1 and RMM2 and make sure that after the peak convection happens here, day 10 and 20 and so on, you get the MJO signal here so that you are not mixing those signals with other signals. That's just the way we do it, which I won't dwell on. So looking now into the Western Pacific, this is day 0 when the convection is maximum here. And you can see there is precipitation maximum there. That is the color shades are precipitation and the red lines are the OLR. Day 10, clearly the OLR and the rainfall have moved into the South Pacific convergence zone. And by day 20, you still have a strong signal. And by day 25, it's basically disappeared. Okay, so at least visually, you can see that the detoured MJOs clearly move into the SPCZ and they enhance the rain at the MJO time scale. Okay, you can look at the anomalous winds associated with them and the OLR, and you see that there's a very clear cross-equatorial flow happening. And that's the contribution to the rain by the detoured MJOs, which is a significant fraction. Non-detoured MJOs do not have that strong cross-equatorial flow, and they don't have a strong rainfall signal like the detoured MJOs do. Okay, so obviously you can do again the advection of humidity, mean and MJO time scale. And I hope you can see these. This is the mean meridional advection of the mean background humidity. And this is the meridional advection of the background humidity by the MJO related wind anomalies. And MJO related wind anomalies have a fairly strong contribution in the SPCZ to the precipitation. So that's the term that I'm showing here and split into seasonal timescale, MJO timescale, and then the higher frequencies are not shown here. They are residuals. Okay, so hopefully it's convincing that this actually makes a contribution. You can also look at the dry static energy advection just to make Adam happy because he always wants moist static energy done in total. And you can see that there is a strong total advection of dry static energy into the southern hemisphere. And of course, there's a vertical advection of the moist static energy and dry static energy as well. Okay. Then the impact also kind of manifests in Rossby waves emanating at MJO timescale from this region. So solving the standard Rossby wave rate tracing, we do that in two ways. I'll show the next plot, but here basically you seed the SPCZ region with different wave numbers that correspond to MJOs and different periods, and see that the paths go over into the Indian Ocean or northwest and northeast, but they tend to seem to avoid the Australian continent here. Okay, these are the wind anomalies, MJO-related wind anomalies as a difference between non-detoured and detoured MJOs. But if you use in this calculation the background winds, actually the difference here is the seasonal winds and the MJO-detoured winds, just to get the seasonality right, not the non-detoured and detoured. Sorry about that, okay? So if, on the other hand, you seed the same region using the background seasonal winds, you can see that the Rossby wave paths cross plenty across Australia. So it is possible that the detoured MJOs are coming into the SPCZ and then having also a remote impact on Australia. I think Harry Hendon has looked at various aspects of air-sea interaction of the MJOs. He wasn't specifically talking about detoured MJOs, but he was arguing that MJOs go across here and they have an impact on Australian monsoon and so on. But this is just another way of saying that. I think I'm coming kind of up to 45 minutes here, even though Arnold wasted some time in the beginning. I would just summarize it this way. So there are mean westerlies in the region here where the MJOs are coming and detouring. And the main mechanism seems to be very local. There is no signature on the Indian Ocean side prior to the detouring happens. So somehow SSTs are generated here, maybe because of this exchange between Karimata Strait and the Java Seas and the sea and the flow of the Macassar Strait or some other mechanism. We have to verify that. And the MJO-related winds and the cyclonic circulation actually enhance the latent heat loss on the northern side and reduce the latent heat loss on the southern side, which allows the warmer SSTs to move southward and the cyclone to move southward. The SSTs are warm here, but they're never warm enough to directly trigger convection from what little atmospheric dynamics I understand. But they can generate the cyclonic circulation and do the moist static energy convergence, and then atmospheric instabilities can then trigger convection. The detoured MJOs then move on into the West Pacific and seem to have a very clear impact on the SPCZ. What is not complete yet is in our story is that if there is in fact cross-equatorial energy transport, what does that mean for the whole problem of energy transport and the IPCZ position and so on that Sarah Kang and John Chang and Tapio Schneider and so on talk about. Sarah Kang has a new paper, I think last year, which talks about the role of the Ekman transport in the cross-equatorial energy transport, in addition to the energy equator that the IPCZ is supposed to be. So that part has to be done as well. But basically that's the main story of this talk. The second paper, as I said, is revised, but the first paper is out that I can send if people are interested in. And I'll stop here and see if there are any questions from anybody. Can I see who's logged in?
Thanks so much, Raghu.
That was fantastic.
Adam has got his hands up. I can see he's ready to pounce.
Adam,
don't attack me, man. I'm an ocean guy. I don't know atmosphere, Adam.
The students are supposed to go first, though, I think.
Oh, really? Okay.
That's colloquium. We don't enforce that here.
Well, I would defer to them if there are any.
Go, Adam.
Okay, so great talk. Thank you, Raghu. So I guess it's sort of two questions that are sort of related. One is, as you know, in the Northern Hemisphere summer, we have the boreal summer interseasonal oscillation and the MJO, which form, I mean, we still debate how similar or different they are, but a lot of events do go poleward even more in the Northern Hemisphere in that season than as what you're describing here. And there has been some argument for an ocean role in that. I'm not convinced at this moment that it's huge, but it may be something. And I'm just wondering if and I think it's a wind evaporation argument, although at least that's how I've understood it, or how we've seen it in some of our own work. I'm just wondering if, how similar or different it is. It seems to me that the through flow and all that stuff is not, is going to be more relevant in this season than in the northern season. And so maybe it's just different, but it looks similar enough that I'm just curious. And the second question, which is related, is like, you're using RMM to, it's just how much in these southern events, as it crosses into the Pacific, how much of the, how completely off the equator is it? In other words, you're using RMM to define the events, and RMM is based on almost totally on zonal winds in the equator. I mean, I think it's 5 north to 5 south. No, it's 50. What is it?
No, that's 15 as well.
Okay, 15, but it's still equatorially centered. I'm just wondering, like, when these things get into the Pacific, like, do they still project on the equator to the extent that others do? I mean, a lot of northern winter MJO events this season, as they go across and they get into the Pacific, there's an equatorial signal that looks kind of like a dry Kelvin wave, and it speeds up and it gets over, the Eastern Pacific and the Atlantic. And is that still there in these events, or have they really, diverted off the equator enough that you don't see that? Which is kind of what happens in the northern summer, that you really lose that equatorial signal a lot of the time.
All right. So the northern summer story, actually, I don't know if you're aware, Lay may be logged in, but he wrote a series of papers on something he calls Central Indian Ocean mode, where he argues a coupled zonal wind SST mode in the Central Indian Ocean, where barotropic energy is claimed to be the source of eddy kinetic energy. And that combined EOF of SST and zonal winds actually can also explain the winter kinetic energy. So I think there is Bin Wang's group also, which has produced the so-called unified MJO index, which tries to explain both seasons. So the role of the ocean, I think, is certainly remarkably different in the two, because the Southern Indian Ocean is not as warm in the MJO season as the Northern Indian Ocean is in the boreal summer, plus the South China Sea is also fairly warm. So in general, the ocean itself is not a big player, and that's why maybe the SSTs in the Indonesian seas themselves, or between Java and Australia, are specifically very prone to get warm enough, okay? As for what happens after they go off into the SPCZ region, we haven't specifically looked at the RMM. We used RMM just because the reviewers won't let you get away without mentioning RMM in an MJO paper. And then it was a whole debate about why don't you use RMM and not RMM? Why are you using RMM1? And we had to struggle to explain that because we are focused on the convection maximum or the maritime continent, and RMM1 is needed for that. But there is definitely a signature in RMM, because to the extent that RMM captures all MJOs, you do have an RMM signature there. But typically, as I said before, when you average over 15 south, 15 north, I suspect there's a lot of misinterpretation that they are dying over the maritime continent or weakening, because you are losing most of the signature at the edge of 15 south. So it may be worth exploring what's happening there. But we definitely will look at the Kelvin waves. That's a good question. I don't know if it's so far south that the Kelvin wave signature is lost, but yeah, we'll have to look at that one. That's a good question.
Thanks. Just one closing comment. We like the OMI index, George Kalatis's, which uses only OLR, and the EOFs vary with season, so that it captures the various poleward deflections a bit more.
I agree. I think definitely something is needed that captures the seasonality of this time scale and not split it into MISO, because MISO has now its own cottage industry of trying to define indices, and Harry Hendon really complains about the MISO index, that it's not predictive, it's diagnostic and so on. But obviously he doesn't want RMM to lose its shade anyway. Joke.
Thanks.
Yeah, I think we have time for one more question, if anyone has one.
I can ask a question if no one. Yeah, that was a great talk. You know, you got a lot of the things right. The anyway, you know, so I just sent you some papers, one published last year. The MJOs have a big effect on the surface layer flow in Mikasa, and that's, you know, that's the part that carries the heat, and so that the MJOs have an imprint on the freshwater plug that you spoke about. And so more heat, and we see a lot of interannual variability of the surface layer flow, not just related to ENSO, which is what we published earlier, but related to the intensity of the MJOs. So it'll be interesting to sort of look a little bit further into that. And I sent you some of the 2019 papers, and also working on another one now. And I think there might be a connection there.
I think, yeah, I agree. I mean, I think maritime continent is really a fascinating place. If you look at Dr. Chen's paper on this Indo-Pacific tripole that he calls, the center mode where huge convection happens, and the ocean there is so critical. And I wish there were some smart oceanographers working in that region. But, I got you back.
I'm going to contact you. I'll send you some stuff, and let's interact on this, because we might actually be able to develop some of that.
All right. Does Mark have a question? Mark?
Unmute.
It seems like he wants to say something, but.
Who, me?
Yeah. Okay.
No. That was a very, very nice talk.
Thank you.
Put it together, and it's an interesting idea, and I don't know. Well, we'll see if the through flow has anything at all to do with it, but.
No, when I give the talk elsewhere, I don't mention through flow at all.
Okay. Okay. So that's the Arnold Gordon special.
That's right.
Fair enough. He deserves it.
All right. Thank you all.
Okay. Thank you very much.
I was just going to, great talk. Were you able, maybe I missed it, but were you able to use any surface heat flux data to confirm the link between the wind anomalies and the sea surface temperatures?
Yes, so we used the latent heat flux to the north and south, and the increased wind speed to the north, reducing latent heat loss and decreasing it to the south. To that extent, yes, but I think we need to run a good ocean model to do that properly. We have to think carefully about how you would do it in a forced ocean model. So that's where we are kind of struggling a little bit. Doing a full coupled model is a pain, of course, but there must be a smart way to do that in the forced ocean model. But we looked at it just for the sake of the relation between the cyclonic MJO winds, background winds, and the latent heat loss.
Great, thanks.
Right.
Okay.
Good.
And sadly, we're out of time, but thank you for a very stimulating talk.
Thank you all.
Fantastic.
Okay.
Stay
Bye,
safe.
Raghu.
Bye, Mark. Good to see you.
Bye.
Good to see you. Good to see you all.
Bye, Raghu.
Bye.
You can hop on here. Huh?
Hey, Chris. Good to see you, man.
Good to see you too.
Hey, you've got gray over there. COVID is getting to you.
This right here?
Yeah.
It's gray, yes.
Oh, man. All right.
We'll talk soon.
Yeah. See you. Nice
care.
to see you. Good to see you. Bye.
Hey, Lagu.
Hey, Gidon.
Yes.
We have to talk. I think Mark should arrange a Zoom for us. Maybe he will.
Yes, I know. Anyways, I just wanted to say hi and thank you. It was
great to hear from you, Gidon.
Same here, man.
All right. Say hi to Laura and the kids.
Thank you. Will do. Take care.
All right. Love you all. Bye.
Bye.